If you remember, the solution to a two-variable system was a coordinate point representing x and y. And so it was the place where two lines intersected on a single plane, the way we'd been doing this since Algebra 1. But we can also solve systems in 3 dimensions, so like length times width times height, or like actual projectile motion where there's a depth, a height, and a width, all of those sorts of things. That's a 3-variable system. And the solution to a 3-variable system is not where 2 lines intersect, it's where 3 planes intersect. So we have our x plane, we have our, well, I guess this would be x plane, we have our y plane, and then we have our z plane. So you have a 3-dimensional figure, and you're finding the coordinate point, the coordinate triple, so x, y, and z, where all 3 of these planes intersect. So now when we're dealing with 3-variable systems, a solution to a 3-variable system is an ordered triple, x, y, z. So first things first, let's just make sure we know how to check our work. I pretty much skipped this in most of what we did last time because plugging in an x and a y is really pretty simple. But as a reminder, it's a little bit different when it comes to 3-variable systems. To show that an ordered triple or an ordered pair for a 2-variable system is a solution to the system, what we have to do is plug in the x, the y, and the z, so this is x, this is y, this is z, into all of the equations and make sure they come up with true mathematical statements. So all day, it's going to be very helpful if we keep our notes nice and organized and we label what we're working with. So this is going to be equation 1, this is equation 2, and this is equation 3. To check that an ordered triple is a solution, which I highly recommend doing on every test or quiz that you have, that when you don't have like an answer key showing, you're going to take the x, the y, and the z, and you're going to plug it into the first equation. So I would write this as x plus 2 times y minus 3 times z equal to 9. So I've just taken the first equation and plugged in the ordered triple, x, y, and z. I just need to do a little bit of math here. This is -1, this is +4, and this is +6. If we add -1 plus 4 plus 6, 4 plus 6 is 10, 10 minus 1 is 9. So we get 9 equal 9, and we're off to a good start. This has to be true for all 3 equations in a 3-variable system, or both equations in a 2-variable system for your solution to be correct. So next we check x, y, and z being plugged into the second equation. Again, just plugging in the values. We'd have 2 times -1 plus, just kidding, minus 2 plus 2 times -2 equal to -8. And we're just going to verify that this actually works. 2 times -1 is -2, then we drop down the -2, and this is -4. -2 minus 2 minus 4 is -8. So we're showing our work to verify that the ordered triple works in that equation. And then last but not least, we're plugging x, y, and z into the third equation. Again, just to verify that that does come out to be true. So this is going to be -1 plus 3 times 2 minus 4 times -2, and we're hoping that's equal to +15. -1 is +1, 3 times 2 is 6, -4 times -2 is +8. 6 plus 1 plus 8, so that's 7 plus 8 is 15. So since the ordered triple works in all 3 equations, that is enough to show me, that's what it's asking, show that the ordered triple is a solution. So you show the work to get 3 check marks by plugging in the x, y, and z into the first, second, and third equation. Again, especially on the test that you're going to take, this is how you'll check your work to make sure you've done the problem correctly in case you're worried that you did it wrong. You're verifying that your solution is correct. Does that sound familiar for how we checked things in the past? It's just that this time we have 3 variables that we're checking instead of just 2. Yeah, so far all we've done is checked a solution. Now, how do we find the solution, you might ask? Thank you so much for asking. We're going to flip it over and we're going to follow these steps. The steps for solving systems of linear equations in 3 variables by eliminating variables. So we're going to be using that addition method from last class. You can solve 3-variable systems with substitution. It's just gnarly. I always recommend using addition for this, especially if you're going to go into anything in a STEM field. If you ever take linear algebra, then we're prepping for the linear algebra skills by doing it this way. So that class will be easy for you in the future. Step 1, you're going to reduce the system to 2 equations and 2 variables by taking 2 different pairs of equations and using the addition method to eliminate the same variable from both pairs. So you want to look for an easy variable to cancel out of 2 pairs of equations. Because when you take your 3-variable system and eliminate it down to a 2-variable system, you now create what we did last class, and you're going to be able to solve the system using addition or subtraction like we did last class. So that would be the adding thing where we add the 2 equations together when their variables are opposites to eliminate a variable, and then back substitute the value of the variable found in step 2 into any of the solved for 2-variable systems. And then you're going to back substitute again to find the 3rd missing variable. These steps don't really make sense until you start to see it, but the goal is to eliminate the same variable from both equations and slowly but surely eliminate down till you have one answer, then plug it in, then plug it in. Okay, I recommend using your nicest, neatest handwriting on these problems. We're going to make columns, so there's 2 problems here that we're going to solve. It all fits on this paper if you organize your thoughts. If you need extra paper because you do not have small handwriting, that is totally available. I actually think, is this on a back or a front of a page? Front, perfect. So you have the whole back in case you need that. But I think we can fit it all in here. Okay, we're going to solve this system. The first thing we always do is label. This is equation 1, this is equation 2, this is equation 3. We want to eliminate a particular variable from one of these equations. My spidey senses say right now it would be easiest to probably get those z's to cancel out because they're already opposite signs. And if I multiply the second one by 2, they'd end up with the same coefficient, yes? So that's what I'm going to do. I'm going to take the first equation and double the second equation, and I'm going to add like I did last class. This is 5x minus 2y minus 4z equal to 3, and 6x plus 6y plus 4z equal to negative 6. So exactly like I did last class where I just multiplied a scalar by everything in that equation, I do that again. We add to create a 2-variable system. Our new equation here is 11x plus 4y, boom, equal to negative 3. Last class when we did this step, we were already down to 1 variable. This class, we still have 2 variables. So we're going to come over here and we're going to label this equation 4. We've created a new system that we're going to be working with. Now, I need to take another pair of the original equations and cancel out z. Would y'all like to cancel out 1 and 3 or 2 and 3? Great. Awesome, because that's what I did in my notes anyways. We'll do 2 and 3 as well. If I want equation 2 and equation 3 to cancel out the z variable, the same variable I did earlier, what would I need to multiply both of them by?
2 by negative 3.
I agree.
3 by 2.
Very good. If we do this, we'll end up with opposite like terms in the z's, meaning we'll have negative 9x minus 9y minus 6z equal to positive 9 for the second equation, and negative 4x plus 10y plus 6z equal to 6 for the second equation, third equation. Okay, we eliminate those z's. Get rid of them. We don't want to work with them anymore. We end up with negative 13x plus 1y, cancel out, equal to 15. This is now equation 5. Once we have this 2-variable system, this lullaby's a little loud today. Once we have this this two variable system, we need to eliminate a variable like we did last class, but we're pretending we only have equations 4 and 5, the two variables that are left. Is there a way to cancel out a variable from 4 and 5 that's pretty easy? Yeah, which one, the x's or the y's? The y would be pretty easy to cancel out. If this one's 4, what would I multiply this by to make it cancel out? Negative 4. So what I'm going to do now is I'm going to take equation 4 and I'm going to multiply the fifth equation by negative 4 so that the y's cancel out. So we write down 11x plus 4y equal to negative 3. And then negative 13 times negative 4 is positive 52 minus 4y equal to negative 60. We continue to solve just like we did last class now, where when we add these equations together this time, the y's will cancel out and we're left with 63x equal to negative 63. So what is x equal to? Amazing, we're a third of the way there. Because we found one of the 3 variables we need. Yeah, if you need more, you can just take over that second column if you wrote too big and just use the entire back for the second problem if you want. Okay, at this point, we need to start back substituting. You can back substitute the letter number, what? Oh my gosh, words. The number we got for x into either equation 4 or equation 5. So we're going to take x and we're going to plug it into, I'm just going to pick equation 4. You could have picked 5 if you wanted, but whatever. Which means we're going to have 11 times this negative 1 we just found plus 4y equal to negative 3. So that's negative 11 plus 4y equal to negative 3. That's 4y equal to positive 8. Add 11 to both sides. Therefore, y is equal to 2. 2/3 of the way there. We found x, we found y. What's left to find? Z. So we're going to take the x and we're going to take the y and we're going to plug it into any of the original equations, 1, 2, or 3. It does not matter which one you plug it into. Which one would y'all like to plug it into? Sure, we'll plug it into 3. Which means we're doing negative 2 times negative 1. That's a back substitution moment. Plus 5 times 2. Plus 3 times z equal to 3. This is 2 plus 10 plus 3z equal to 3. That's 12 plus 3z equal to 3. Subtract 12 from both sides. You have 3z equal to negative 9. Divide by 3. Woo-wee. Z is equal to negative 3. Goodness gracious, which means we finally made it to the conclusion that x is negative 1, y is 2, and z is negative 3. That's our ordered triple that solves the system. Okay. This is when I'm normally like comments, questions, and concerns and nobody says anything. So what we're going to do is we're going to walk it step by step and I'm going to ask multiple times comments, questions, or concerns. Okay, that probably is better. So what did we do very, very first?
We combined 2 equations.
We combined 2 equations with the goal to do what? Get rid of any of the variables. It was easiest to get rid of z because I could kind of tell that these were going to cancel with very little manipulation. Amazing. So we did that. What did we do after we canceled the z out from 1 and 2?
You added the third equation, and then you canceled out. No. You added the third equation.
Yeah, cancel out the
And cancel out the other zero.
Yeah, we need to cancel out z in a different pair. So we used the first pair was 1 and 2. You could use 1 and 3, or you could use 2 and 3. Doesn't matter, as long as it's another pair of functions that you're canceling out the same variable. After we do that part, so it's basically like repeating the same step twice to eliminate one of the variables. We had 2 new equations, equation 4 and 5. What did we do? What was our goal with equation 4 and 5?
I want to remove one.
To remove another one of the variables, to get another variable to cancel out. So in this case, y would be easiest to cancel out. So we made it to where the two equations would cancel out the y. Then we just started plugging back in. So once we got one of the variables x, we used the smaller equations 4 and 5 to find one of the other variables, y. And then we used x and y in one of the original, doesn't matter which one, to find the last variable which we first eliminated. You do not have to eliminate y's or z's first. You might be eliminating the x's first. At that point, you're just mathematician's choice of what you see and what would be easiest. Yes?
Why did you use the 11x instead of like an original?
On this step,
Yes.
What-
The variable's already gone and it's easier to solve for the one.
yeah, when you have only one variable, you can only solve for another variable if there are two. So we didn't want to plug it into one of the original ones because there were two missing variables there. We just want to use something that only has one missing variable. I could have used number 5, equation 5, but I just go in number order usually. That's my habit. Other questions? Can we see another example? Cool. No, we're going to do it anyways. Example 2, part 2. We're still solving a system. Do you notice something different about this system compared to the one we just did?
There's already one with just two variables.
There's already one where a variable has been canceled out. What variable was canceled out? Y. So our goal now this time is we're not going to have to repeat that very first step twice because we technically already have one equation with two missing pieces. We need to combine equations 2 and 3 in some way to get the y's to cancel out. You want to eliminate the same variable. What could we do with equations 2 and 3? -2 times the second equation, and then add the third equation. Those y's are going to cancel. That's what was canceled already, so we want to cancel the same thing. So this would be -2x minus 2y minus 4z equal to -34. And then x plus 2y plus z equal to 16. We're eliminating the same variable that's already missing. Fabulous. So that means we have -1x, the y's cancel, plus, just kidding, minus 3z equal to -18. This is equation 4. I don't have to make an equation 5 like I did in the first example because I already have two equations in the same variables. Equation 1 and equation 4 are already with just the same variables.
You can already do it because the x's and the x's cancel.
Yeah, so this one's nice. I don't have to even manipulate equation number 1, x plus z equal to 8, and -x minus 3z equal to -18, because you're right, the x's would already cancel out. All we have to do here is combine them. X's are gone. We have -2z equal to -10, which means that z is positive, but yeah, +5. We're already at the point where we have one of the variables. What do we do to solve for the next variable? Plug it into one of the ones that has two variables in it. So you could plug it into number 1 or you could plug it into number 4. I like to go in number order because I just can't help myself, so I'm going to plug it into number 1. I'm using 1 because it only has the two variables in it, which means I'm doing x plus 5 equal to 8. That's my back substitute moment. Let me make that look nicer. And if x plus 5 is equal to 8, what is x equal to? 3. I now have two of the variables. Now I'm plugging them both in. To which equation? Number 2. Should I plug them into 1? No, it wouldn't help me find y. That's what I'm missing. So I'm going to plug them into number 2 You could plug them into number 3 if you wanted to, but this ends up being 3 plus 2, no, just y. 3 plus y plus 2 times z equal to 17, which is 3 plus y plus 10 equal to 17, or y plus 13 equal to 17. So what is y equal to? 4. So our ordered triple here is 3, 4, 5. You did not solve for them in order, in alphabetical order. That doesn't matter. But you answer in alphabetical order. X, y, z. It's an ordered triple. And that, my friends, is solving 3 variable systems. Individually, the steps are not hard. It's overwhelming to look at a problem from start to finish, but individually, these steps are not too hard. Y'all did great last class. Those are the same skills that we're using this class. We're just adding a couple extra steps. You're welcome.